All right, so this is the last lecture of Math 313 number theory. I do not remember exactly how this came to be, but there was a discussion with a subset of students in this class about giving an entire lecture as Dr. Seuss. I do not believe I will be able to make it an entire lecture. I've had too many things come up during the semester, and as you guys procrastinate to the last minute, to some extent this has happened to me as well. And a couple of issues with some committees I'm on took 3 or 4 extra hours yesterday, including forcing me to have to walk to the elementary school in the middle of the day to see if my son is available for a very quick makeup game. My wife was not thrilled that this is the best use of someone's school time. My son thought this was absolutely terrific to be pulled out of class and asked, are you available to play and pitch today? All right, so I will try to do the lecture as Dr. Seuss as long as I can. My kids and I have tried to prepare. Hopefully the video is far enough away that this is not going to be truly visible. Anybody know where I went to graduate school? Princeton. And so this is one of the, we're doing the Dr. Seuss lecture. I wish I could recall how I promised, or why I promised to do this, but a promise is a promise. I could go into like Horton Hears a Who. So you can try to figure out which Dr. Seuss stories my kids and I have been using to build this lecture. At various times, like all my lectures, I will ask you to participate. If you can, please participate in Seussisms yourself. A lot of times it should hopefully be apparent what you should answer either by mathematical reasoning or by your knowledge of Dr. Seuss. I do remember having a Seuss rumble with one of my colleagues, Joe Silverman, years ago to see who could do The Cat in the Hat better. And it was embarrassing. I could do about a quarter of the book from memory. His kids were significantly older than mine, but he had read The Cat in the Hat so many times, he still beat me. Okay. Anybody know what we're studying today mathematically? The circle method. Well, because what's the circle method used for? What's the type of problem we're trying to study? So I did mention months ago what we were going to use this for. This is for writing numbers as a sum of primes. So just before the lecture begins, you might ask, who the hell cares? Why would you want to write something as sums of primes? Well, okay, well, good. So Alex cares, and we care about Alex. Therefore, we care about writing numbers as sums of primes. If you look at Fermat's last theorem, which we did over polynomials last time, x to the n plus y to the n equals z to the n. If you let maybe Sn be the set of non-zero nth powers, what we're showing is basically Sn plus Sn intersected with Sn is not empty. That there's some number which is a sum of 2 nth powers. Or, since Fermat's last theorem says that it is empty if n is greater than or equal to 3, we're trying to get some information about this. When we're doing things about writing things as sums of primes, we're trying to do something very similar. If you let P be the set of primes, we're looking at what can you say about P plus P? What numbers would this be? What about P plus P plus P? What would that be? And just so on and so on. And there's a whole slew of problems like this. We did Waring's problem, which is what if you want to look at some fixed number of sums of squares, cubes, fourth powers, and you allow yourself to have more than just 2, 3, 4 terms. As you add more and more terms, what do you think should typically happen?
The number of numbers you make gets bigger.
Usually the number of numbers you should make should get bigger, but what would you love your set to have for that to be true? Because you could actually have some problems that as you add more and more numbers, the number of numbers you get can become smaller. So let's let our set S be the numbers 2, 3, 4. And let's look at S plus S. What is S plus S?
4.
Yeah.
5, 7, 6.
6.
7.
So when I add S to itself, I actually get fewer elements. And if I keep adding S to S to S to S to S, it's going to get small and small and small. What element would you love to have in your set? 0. You'd love to have 0. Right? If you were doing things multiplicatively, we'd like to have 1. And so this is one of the problems. So do you want to consider 0 a prime? If you do, then you can talk about things. I'm writing a number as a sum of at most 2 primes, of at most 3 primes, of at most 4 primes. because you now have that 0. Because you don't have the 0, there is some issues. All right, we ready? All right. I stood there with evens. I stood with primes too. And I said how I wish
I had 0, 2.
I could get all with just 2. Not a bad try. Right, so this is the Goldbach problem. I want to write every even number as the sum of 2 primes. I stood there with evens, I stood with primes too, and I said how I wish I could get all with just 2. The primes are not so dense. They're really quite small. You might think that such a set wouldn't be dense enough at all. Can anybody give me an even number that's not a sum of 2 primes? 2. So there is. So how would we modify this? We're not going to be able to show every even number is the sum of 2 primes. Yeah. So we'll modify this. We need an approach to prove what is expected. Fortunately, Hardy and Littlewood gave us their
Circle method.
Thank you. The method will help us. It has what we need, and its idea is quite simple, and it works at great speed. And with 4 primes, it's 100% guaranteed. Can anybody detect which story? Curious to see how well people know their Seusses. Sneetches? No. So Fn of x is going to be the sum over all primes less than or equal to n e to the 2 pi I px. This is going to be our generating function. And again, it's taking something that's local and building up and making it global. Sometimes you put a log p in front of the exponential. And the reason you do this is it makes the analysis a lot easier. When we count primes, it's better to discriminate slightly. This is one of the few cases in your life where it's okay to discriminate. As long as it's not massive discrimination. You can give a small little bump. And that bump might make you cat in the hat. How that bump made us jump. Yes. All right. So in complex analysis next year, I will talk about why you put log p's if you're interested in something like that. It just makes the counting a lot nicer, a lot smoother. It means the small primes have a lower weight, which is good because things that are fluctuating there. And we know that the correct scale to study the primes is about log p. I'm going to just ignore this because this is just meant to be a heuristic lecture. We will pick up the primes. You will see something new. 2 terms, and we call them almost. 2 terms, and we call them nope. F1 and F2 is not bad. I'm glad you didn't say something else that rhymes with 2 following F. This is supposed to be a appropriate Dr. Seuss. We will pick up the primes. You will see something new. 2 terms, and we call them no, term 1 and term 2, right? You could call them F1 and F2 as well. So what we're going to do is we want to write I'm sorry?
Term red and term blue.
You could do term red and term blue. So the idea is the following. If I square fn of x, this is going to be the sum p1, p2 less than or equal to n of e to the 2 pi I p1 plus p2x. Because when I multiply everything, I'll have the sum twice, and the product of two exponentials is just add the exponents. Okay? And now what I'm going to do is I'm going to integrate this from 0 to 1, and I will multiply by e to the negative 2 pi I 2nx dx. Integral from 0 to 1 of e to the negative 2 pi I 2nx dx. What's the integral of a sum? Sum of the integrals. So this is going to become a sum p1, p2 less than or equal to n. Integral 0 to 1 e to the 2 pi I p1 plus p2 minus 2n x dx. What's the easiest value of p1 plus p2 minus 2n to analyze? Yeah, if this is 0, then I get 1. If it's not 0, I have a cosine and a sine. Remember, e to the I theta is cosine theta plus I sine theta. And so if I have e to the 2 pi im, that's cosine mx, I guess 2 pi mx, plus I sine 2 pi mx. When you integrate a cosine over a whole cycle, what do you get? 0. What do you get when you integrate a sine over a whole cycle? Unless m equals 0. If m equals 0, cosine of 0 is 1, sine of 0 is 0. So what happens here is the only term that survives is when p1 plus p2 equals 2n. So this is going to just be the number of pairs of primes p1, p2, each less than or equal to n, and they sum to 2n. This integral is the answer. If I want to know, can I write my number 2n as a sum of two primes? Well, all I have to do is if I choose my big N so large, let's say I choose n to be 2n, I'm not going to need a prime larger than 2n to write as a sum of two primes. I'm not going to write 38 as a sum of two primes where one of the primes is in the 70s. Right? So all we have to do is evaluate this integral. You've taken 3 classes on integration. Right? We have reduced the Goldbach conjecture. The Goldbach conjecture is every even number is the sum of two primes if the number is big, like 4, to an integral. The Ternary Goldbach is actually a theorem now. Every large odd number is the sum of 3 primes. Anybody know what large means? No. We're not talking about odd numbers. Every large odd number is the sum of 3 primes. So can you write 5 as the sum of 3 primes? No. What about 7? Can you write 7 as the sum of 3 primes? Yes, 7 is the sum of 3 primes. So 7 is actually the answer. Once you are at least 7, you can be written as the sum of 3 primes.
Sorry, how do you write 7 as a sum of?
2 plus 2 plus 3.
Oh, it doesn't have to be distinct.
It doesn't have to be distinct. They don't have to be odd primes. If you can write every odd number as the sum of 3 primes, that has some interesting consequences. So this is the generating function. This is an idea we've been seeing all semester. And I do apologize for not being 100% in Seuss. There was no time. All right? Local information, building it up, getting a global object, and trying to extract information from it. The local information is what's going on at each prime. We bundle them together and we have this function. Now, when you hear the phrase circle method, what do you think of? Elliptic curves. I was going to say you got a 50-50 chance there's only 2 words. When you hear circle method, what do you think of? Circles, right? There's actually no circles in the circle method anymore. They've removed all the circles from the circle method. And the reason is that instead of looking at a circle like this, you can look at a wrapped around unit interval. And you can look at numbers modulo 1. And we've done a lot of things with modular arithmetic looking at numbers mod 1. So here's 0, 1. Or I can have my angle going from 0 to 1, wrapping it around like this, or 0 to 2 pi. Depending on where you are, you use different notations, different intervals. It really makes no difference if you go 0 to 2 pi, 0, 1, wrapped circle. It's all roughly the same. And the idea is we want to understand this integral. So we're going to break this integral up into 2 parts. One part is going to be where the function is large and has a significant contribution. The other part is going to be where the function is hopefully smaller and will have a smaller contribution. If we want to show that I can write my number as a sum of 2 primes, what do I have to show about this integral? Or can you tell me anything about this integral? What kind of number is this integral? It's an integer. What do you want to show about this integer? Could it be an integer like -12? No, it's the number of ways we can do something. This is a non-negative integer. Right? All we want to do is show that it's not what? As long as we can show the integral is not 0, that's all we have to do. All we have to do is show the integral is not 0 and we win. So if we show that the integral is at least 0.6, would that be enough? Yeah, it's got to be an integer. If it's at least 0.6, it's at least 1. What if we show the integral is at least 10 to the negative 1,000 factorial? Is that enough? Yes. We just have to eliminate 0. So what we're going to do is we're going to break this integral up into 2 parts. And the goal is to show that the main term is larger than the error term. And that we can bound this above 0. And if we can bound it above 0, then we win. Unfortunately, we don't have strong enough techniques to do this with 2 primes. We don't have enough freedom. But if you add more primes, we can do so. OK. We will pick up the primes. You will see something new. 2 terms, and we call them term 1 and term 2. So we have fn of x is the sum p less than equal to n e to the 2 pi I px. What's the easiest choice of x to evaluate this function? If you got to choose an x, what x would you choose? 1. Or a point that's equivalent to 1? -1, but there's another point that's better than -1. 0. I'm sorry?
You could choose x to be 0.
No, it's just e to the 0. What's e to the 0? 1. If I choose x to be any integer, then I have e to the 2 pi I integer. It's going to just be 1. So if I evaluate this at 0 or at 1, I'm going to just get the number of primes, which is approximately n over log n. What's the next place to evaluate this at? All right, if your phone, you have to provide munchkins now for the next class. So this is actually the best day to have your phone go off. If you want to have friends calling you nonstop, there's really no consequences. What's the next best point to evaluate this? If you had to choose a value of x.
P over 2.
I'm sorry?
P over 2.
Well, x is between 0 and 1, right? 0 less than equal to x less than equal to 1. Where would be the next choice of x? A half. And after half, what would you choose? No, never 1 over pi. A quarter? Really? You'd go to a quarter next? We have 0, we have a half. I can see a quarter, but I think there's something before a quarter. 1/3. Right? So if we try 1/2, we get the sum p less than or equal to n of e to the 2 pi I p divided by 2. All right, this is the sum p less than or equal to n of e to the p pi I. If p is equal to 2, we have e to the 2 pi I, which is 1. If p is an odd prime, we have e to the 3 pi I, 5 pi I, 7 pi I, 11 pi I. What can you tell me about all those values? So what's e to the pi I? What's e to the 3 pi I? What's e to the 5 pi I? -1. So here's 0. Here's e to the I pi over 2, which is just I. Here's e to the I pi, which is -1. Here's e to the 3 pi I over 2, which is minus I. So this is going to just be 1 minus pi of n minus 1, because we have one even prime and all the rest are odds. So this is approximately equal to minus n over log n, plus something really, really small. So we really know what's going on if we take 0, 1, or 1/2. More generally, we could evaluate it at some rational number a over q. And then this would become a sum of p less than or equal to n e to the 2 pi I ap over q. How do you think I would understand ap over q? Yes. Well, so aq is going to be some point on the circle, but I have to execute the sum over primes. So the question is, how strongly do these individual values depend on p? So when you look at this, do I need to know p completely, or do I need to only know p up to some kind of equivalence? Yeah, I only need to know what's going on p mod q. If I increase p by q, I add another 2 pi I. I've gone around the circle another time. So this is really the same as the sum of r mod q, then the sum over primes p less than or equal to n, p congruent to r mod q, e to the 2 pi I ar over q. And so I really only need to understand something like this. Now, here's the interesting question. How does this depend on the prime p? There's no p dependency anymore. All that matters is p congruent to r. For a given congruence class, they all have the same contribution. I can pull this outside the sum. And so I'll get a sum of r mod q e to the 2 pi I ar over q. And now it's just going to be the number of primes congruent to r mod q up to n. And there's a beautiful thing by Dirichlet that says to first order, primes fall evenly. So we'll make this an approximate. And this will be approximately the number of primes divided by phi of q. So this is a nice way to review a lot of the concepts, a lot of the functions we've seen throughout the semester. This is the Euler-Toscan function. It's the number of numbers relatively prime. And when you think about it, if I give you a number like 16, and I want to know what are the possible congruence classes, I need numbers that are relatively prime to 16. What if I give you a number like 34? Do I need numbers relatively prime to 34? Well, what about 17? 17 is not prime to 34. Can there be a prime that's 17? Yes. Can there be infinitely many? No, there can only be one. So if I share a factor with q, there's at most one prime that would share that factor. And that's if that factor is a prime. So in the limit, it's not going to really contribute. So really, I only have to look at the r's that are relatively prime to q. I can say the GCD of r and q equals 1. Because when r and q have a common factor, there's going to be at most one prime. And so what you see now is that this function can be of size pi of n over phi of q. And then you have this factor over here. There's about q terms. Several of you have taken probability with me. These terms are going to be roughly, they're all going to have absolute value 1. They're going to be complex numbers. How big would you expect a sum of terms of size 1 in absolute value? And you have roughly q of them. So you've taken probability, but how large would you expect that sum to be? Got q terms. Each one is of size 1, but the signs can be fluctuating at random. About q. That means complete alignment. So imagine the signs can only be +1 or -1.
Oh, they're not centered on 1.
Nope, they're not centered on. So imagine the signs are +1, -1.
It's 0.
Well, you would expect on average it to be 0, right? What would you expect the size of the fluctuations to be if you have q terms from probability? So we want the standard deviation. So if you flip a fair coin, q times, you expect about q halves heads, q halves tails, and you expect the fluctuations to be of size square root of q. So we expect this sum to be 0 with fluctuations of size square root of q. So we would expect this whole thing to maybe be something of size square root of q over phi of q, which is about q down below. We expect this to be probably on the order of n over log n divided by square root of q. That's a rough estimate, with some kind of signs depending on exactly how that is. What this is telling us is that for a typical rational point, this is a good estimate of its size. What happens as the rational number q gets larger and larger and larger? What can you say about the size of the function? It's going to 0. So we expect this function to be really large near primes with small denominators, near rationals with small denominators. The larger the denominator, the smaller the size of the function. Okay? So we want to get an estimate of the average size of this function. So let's say we want to calculate the average value. And then I promise we will get back to terms 1 and term 2. Okay. So one possibility is I could compute this integral. And that will be the average value. This is one of the worst integrals you could calculate in your life. We have a sum of exponentials, highly oscillatory. They depend on where the primes are located, and we're putting in absolute values. Absolute values are extremely dangerous and hard to work with. How many of you remember the calculus problems where you have to minimize the distance between, say, a point and a curve, or something like that, and you want to figure out something? I have a curve on a line, and I have a parabola, and I want to figure out which point on the line is closest to this point on the parabola, something like that. You never want to minimize distance. What do you want to minimize instead? Why is distance so painful to work with? So what makes distance painful? The square root. How do you get rid of the square root? You square it. And say, look, instead of minimizing the distance, I'm going to minimize the distance squared. Then the calculation is a lot nicer. All right, so let's calculate the average value of fn squared. Turns out this is significantly easier. And the reason is, if I give you a complex number x plus iy, its modulus squared is x plus iy times the complex conjugate x minus iy. And when you expand it out, you get x squared plus y squared. Just the square of the real part plus the square of the imaginary part. So over here, if I want to calculate this, this is the same as the integral from 0 to 1 of the sum p less than or equal to n of e to the 2 pi I px. And now I need the complex conjugate. So I'm going to have to use a different prime. So I'll use q. And it turns out the complex conjugate, all I do is I replace the terms in the exponentials. I replace I with minus I. Because e to the I theta is cosine theta plus I sine theta. I now want cosine theta minus I sine theta. Well, I'll just replace theta with minus theta. So all I have to do is put in a minus sign here. What can you tell me about the integral of a sum? Sum of the integral. So I got a sum of pq less than or equal to n, the integral from 0 to 1 of e to the 2 pi I p minus q of x dx. What's the only time this integral is non-zero? So when would this integral be non-zero? P equals q. If p equals q, I'm just integrating the function 1. If p doesn't equal q, I'm integrating, say, e to the 2 pi I 4x. And that gives me cosine 4x plus I sine 4x. Well, when I integrate cosines and sines over full periods, I get 0. So this integral is going to be of size 1 whenever p equals q and 0 otherwise. So how many times does p equal q? So p's are primes up to n, q are primes up to n. How many times will they be equal? Number of primes. Right? You give me a p, and there is one and only one q. So what this tells us is the average value of fn squared is of size pi of n, or about n over log n. All right, so if the average value of fn squared, this is not quite as good as a physics hat, but it's close enough. If the average value of fn squared is about n over log n, what do you think the average value of fn is? About how big would you guess that would be? Yeah, square root. So square root of n over log n. And now we can begin to see how the circle method is working. If I am near a rational, if I'm near a point a over q, I expect my function to be of size n log n over square root of q. But on average, the function is of size square root of n over log n. So most of the time, the function is roughly of size square root of n. That makes sense. If you think back to probability, if you think back to flipping random coins, I've got a bunch of terms of size 1. I have about n of them. I expect square root cancellation. I expect on average it's 0. I expect fluctuations of size square root of n. It should be roughly of size square root of n. Most of the time, it is of size square root of n. Most of the time, you're getting the cancellation. But every now and then, things align. And when those things align, you get a huge contribution. And so the idea of the circle method is we want to split the integral up into two parts. And we call them the major arcs and the minor arcs. They're called this way because we used to do them on a circle, and we would talk about arcs of a circle. And what you would do is you would take rationals with small denominators, and you would choose little blips around them. And then you would estimate the integral over those major arcs. And then you would estimate the integral over everything that's left over. And those are the term 1 and term 2. All right, so the idea is to show you, how we attack essentially one of the hardest problems in number theory, and to give you an idea of what are the tools and techniques. At the same time, review a lot of what we've done this semester. So what we do is let's MAQ is going to be A over Q minus 1 over g of n, a over q plus 1 over g of n. So what I'm doing is I'm taking a small window about the rational number a over q. And I do not want to go into the technical details right now. There's a window. The size of that window is going to depend on a lot of things. The bigger the window you have, the smaller the stuff that's left over. But then the more accurately you need to be able to estimate your function on that window. If our window is really small, can our function change that much if we move a little bit past a over q? We've got continuity. If the window is sufficiently small, its value at a over q is essentially its value. So we would love to say fn of x is approximately equal to fn of a over q with a really small error. And then if I integrate the function over this arc, it's going to be approximately this value times the length. Turns out we do a little bit more than this. We do a little bit better approximation than just the first term. We find a function that agrees with fn at a over q, and then we bound their difference, and it turns out that the function we find is easy to integrate. And then we get a contribution, and then we sum. And so term 1 is going to be a sum of all q up to some big Q, which is a function of n. A sum over all a relatively prime to q. An integral from 0 to 1 of fn of x squared e to the negative 2 pi I n, 2n x dx. And then term 2 turning as I walk behind, which is nice.
What in that speech?
Okay, good. All right. So this is our term 1. This is term 2. We need to show that term 1 is much larger than term 2. Actually, we don't. We just need to show it's larger than term 1 and have this term 1 enough to push us above 0. Okay, at first you won't know just what you need to do to ensure that term 1 is much larger than term 2. The error term shouldn't contribute. We must make it small. It should not be seeable as the main terms almost all. This is where things get extremely technical. It takes a lot of work to show that you have enough cancellation with this. The problem is the major arcs over here are very small. It's a very small window, so almost all of the unit interval is in the minor arcs, is in the error term. So you're integrating over almost every point, but the function is small. Over here, you're integrating over a very small set, but the function is large. So you have this, you're being pulled in two different ways. And the hope is that you can do things well enough so that the pull of this will balance this. And this is where it really gets technical. How big do you want to make g of n? The bigger you make g of n, then the less there is in the minor arcs, which is good. It's going to decrease the size, but then you're going to have more oscillation in the major arcs, and you can't approximate it as well like this. Okay. The first term is a good term. It is tame, oh so tame. It shows right here what we expect to be true, that every even number is a sum of prime 1 and prime 2. Here is the game that you should all like. We approximate the value by looking at small spikes. There that the sum runs about with big bumps, jumps, and ticks, and with a little care and all kinds of good tricks. We do like the way that issues go away. If only term 2 were like this, oh, what we would say. Anyone know which one that's from?
Maybe Places You'll Go?
I was trying to remember if this was from the Places You'll Go. My feeling was I pulled that from all the Places You'll Go in honor of some of you graduating, assuming you do well in the final. Yeah, for those of you who are juniors, it doesn't matter so much if you do well in the finals because you've got another chance next year. So the problem is the techniques we use for term 1 do not work for term 2. We look up and down terms 2 sum, we look them over with care, we try many approaches, but none are good enough to compare. Albeit things can happen and frequently do, 2 sums as variable and wild as term 2. Oh yeah, then this is definitely all the places you can go at this point, yes. Okay, the sum just taunts us as we try our approaches. After each attempt, all that's left of approaches. We never have learned it's so big it encroaches. So this is the problem. How do we estimate term 2? The only way we really know how to estimate something like this is to shove in absolute values. So what I want to try to do is give you a sense of why it is so much harder to do sums of 2 primes than sums of 3 primes. This is a very long, complicated theorem, but it's possible to get a flavor of what's going on. So when you look at term 2, we want to show term 2 is small. We have an integral that's highly variable. And so we want to approximate it. So we want to integrate over 0, 1 minus the major arcs of fn of x squared times e to the negative 2 pi I 2n x dx. And essentially, what's the only thing you know how to do if you want to approximate the absolute value of an integral? What would you bound it by? So we have an absolute value of an integral that's less than or equal to the integral of the absolute value. Is you shove the absolute value inside. You shove the absolute value inside, you now lose all the oscillation from this point. And you get that this is less than or equal to the integral over 0, 1 minus the major arc of fn of x squared dx. Well, because this is almost all of the interval 0, 1, this is the integral over 0, 1 of fn of x squared dx, which is about n over log n. And it turns out this gives you too large of a value. When you actually calculate what the main term is, that's essentially the same size as the main term, and you're screwed. I can't use stronger words just as Seuss. What could you do instead? Well, what you could do instead is this was really, it's bad putting in the absolute values in, but we don't know much else to do. And then over here, we used our formula. What we could do is we could do a little bit more first. We could first say that this is less than or equal to the maximum of x in 0, 1 minus the major arc of fn of x times the integral from 0 to 1 of fn of x in absolute value dx. So what I do is I pull out the largest value, and then I extend what is left over to integrating from 0 to 1. And now, if I can get some cancellation over here, we win. The problem is, when you do the analysis, you need the cancellation to be so extreme that the maximum value is less than the average value. You are not going to be able to show the maximum value is less than the average value. Okay, this is a tautology. What can we do better? Well, what we really want to do is we want to exploit cancellation. And as soon as we put in absolute values, things are bad. We lose all the oscillation from this. And now we have this bound over here. What if we had 3 primes? Well, this is the nice thing about being at a blackboard. I can change 2 to 3. I can change 2 to 3. And now I'm left with an integral of fn squared. Can I exploit cancellation here? Yeah, we did so earlier today. We can write this exactly as the function times its complex conjugate. And we know this is small. This is going to be of size n over log n. And so that's the trick, is if we have 3 primes, we can actually survive the approximation here. And now we just need a small savings on the minor arcs, a small savings over here. And we end up winning by some powers of logarithms. It's a very long, delicate analysis, but it is possible. All right, and then to end, we can't do 2 primes. We don't have enough freedom. But with 3 primes, there's hope. That we don't have to be as clever, we don't have to be exploiting the cancellation there. But these fears are quite wrong. I'm quite happy to say, if you're willing to modify what we shall prove on this day, if instead it's decided that we use 3 primes, not 2, and work with odd numbers instead of, if we decide that it won't matter how many sums, that having 4 primes is as good as just 2n, in that case we can forget about all the errors, and whether each is a sum of 2, 3, or 4 of those. So can you show everything is a sum of 4 primes? Everything large. So how would you show everything is the sum of 4 primes? Okay, so how would you do it? We've got like 3 minutes left to finish. So we know all odds greater than or equal to 7 are a sum of 3 primes. Claim all m sufficiently big sum of 4 primes. How would you do this?
Subtract that of 2 or 3 to get an odd number.
Okay, so if m is odd, what should we look at?
n minus 2.
M minus 2, which we know is p1 plus p2 plus p3. We get m is 2 plus p1, p1 plus p2 plus p3 plus p4, which is just 2. What if m is even? Subtract 3. M minus 3 is p1 plus p2 plus p3. Therefore, m is p1 plus p2 plus p3 plus p4. And now p4 is just 3. So the idea is that we can actually go and do 4 primes without any trouble. The difficulty is doing 3 primes. But it's surmountable. The extreme difficulty is doing 2 primes. There's just not enough freedom. You need too much oscillation. Okay, so this is a good place to stop.